In this video, we're going to be talking about differential mass elements and variable mass systems. So imagine I've got this dodecahedron here, and I'd like to measure the energy of it. So assuming it has uniform density, I can take a differential mass element here, dm, and that's going to be equal to rho, or the density, times the differential volume element, dv. If I want to find the energy for the whole dodecahedron, I can merely calculate the energy on each of these individual mass elements, E dm, and sum them up over the entirety of the system. Or since this has uniform mass, I can turn it into a volume integral, so just integrating across the shape of the object. I can do the same thing for force. An example of this would be looking at gravitational force here. So here, the gravitational force on a differential mass element dm would be equal to big G times the mass of the big object times dm divided by the separation squared. Imagine someone tried to dig an elevator to the core of the Earth, and after they excavated all the way down, they discovered, unsurprisingly, that this was a really bad idea. So now we're stuck with this task of filling in the elevator shaft with dirt. So we want to know how much force is necessary at the base in order to hold up this whole tube of dirt. So my differential mass element, this little hockey puck here, is going to be equal to rho times dv, which here is equal to rho, or the density of the dirt, times the cross-sectional area times the differential radius. And so here is the differential radius element, and this is its height above the ground. So if I want to calculate the gravitational force acting on this infinitesimal little hockey puck here, what I can do is I can divide the Earth into two concentric spheres. So imagine that I have one sphere inside sitting at radius r, and then one sphere, or spherical shell, I should say, outside that. And so there is a force coming from the hockey puck sitting on the outside of the sphere of radius r, and we'll calculate that in a sec. But we could also calculate the force of this hockey puck coming from all of the dirt outside. And it turns out that if you have a spherical shell, there is no gravitational force that acts on a body inside. We could do that as a calculation here, but we're just going to take that on faith. The gravitational force acting to hold this infinitesimal mass element up is going to be given by this. So we've got G times 4/3 pi r cubed, so it's the volume of this inside sphere here, times rho, or the density of the Earth, we'll assume is the same as the density of the dirt. The differential mass element here has mass rho times a dr, and it's divided by r squared. Now we can integrate this from the center of the Earth all the way out to its radius to get the total force. This is going to be the integral we need to do, so we pull out all of the constants. We end up with 4/3 GA times rho squared, and we're integrating r dr from the center of the Earth to the crust. And we end up with a force of 2/3 G times A times rho squared times R squared, necessary to keep up the entire tube of dirt. So this is how problems of this form go. Typically, we're not doing a lot of examples in these videos, but this is the basic idea. You take your object, you break it up into infinitesimal mass elements, you calculate the energy or the force, or as we'll see in a moment, the momentum, and then you integrate that over the system. Imagine I have a little rocket, my spaceship is going along in space, it has a mass m, and it's traveling at velocity v naught. And then it decides to turn on its thrusters. So it turns on its thrusters and loses some mass dm, which is traveling at velocity v0 minus u. Now the rocket has lost a little bit of mass and is traveling at a new velocity v. So we want to see how velocity v changes as a function of time. In this case, we're going to assume that the rate of mass loss is constant. So it's turning on the thruster at a constant rate, and we'll just call that rate eta. So we can use conservation of momentum to see how this is going to work out. So our initial momentum is merely m times v naught. And our final momentum is going to be a sum of the momentum coming from the mass lost and the momentum of our ship. So that's going to be dm times v naught minus u plus m minus dm times v naught plus dv. So this is going to be our final v is going to be v naught plus some infinitesimal velocity. So I can look at the change in momentum here. So dp is going to be equal to p final minus p initial. So you'll notice that the mv naught term here can cancel with this mv naught term here, and the dmv naught term and the minus dmv naught term can cancel here. This is equal to minus u times dm plus m times dv. So there is another term minus dm times dv, but this is a double differential, so that term goes to 0. I know that the change in momentum is 0, so this sets me up with a differential equation for velocity as a function of mass lost. So I can write that down. So I can rearrange terms, and so I'm going to integrate dv from my starting velocity to my velocity as a function of mass. U is the speed that the rocket fuel is leaving the thruster with respect to the initial velocity of the rocket. And I'm going to integrate dm over m from my initial mass m to my mass as a function of time. So I'm going to be losing mass at a constant rate coming from this. So that is m minus eta times time. So this is how my mass is decaying over time. So I can integrate this, and I find that velocity as a function of time for my rocket is going to be equal to v naught plus u times the natural log of m divided by m minus eta t. What does this look like? So as t increases, the denominator decreases, which means this whole thing is going to increase. So the total effect of this is that the speed of the rocket is going to increase logarithmically.